In this topic, methods for creating magnets are described, as is a method for visualizing the lines of force surrounding a bar magnet. The behavior of magnetic poles is described. One way of magnetizing a steel or alloy bar is by stroking it with the tip of a bar magnet. Another method is to wrap a coil of insulated wire around the bar to be magnetized and pass a heavy DC current through the coil. In both of these methods, we are exposing the bar to the influence of a strong magnetic field, and it is thought that this process causes the molecules that make up the bar to all line up in the same direction as the magnetic field. Indeed, in certain materials, it is found that when the magnetizing source is removed, the bar still retains its magnetic properties, so becoming a permanent magnet. However, not all materials are so obliging. For example, soft iron or silicon steel lose their magnetic properties as soon as the magnetizing force is switched off. A well-known experiment which is often performed to help us study the magnetic field around a permanent bar magnet consists of placing a sheet of glass over the magnet and sprinkling iron filings onto the glass. It's interesting to note here that the sheet of glass does not act as any form of barrier to the magnetic field. After all, the magnet is placed below the glass, but we can clearly see the effect of the magnetic field above the glass. In other words, materials that provide good electric insulation do not act as insulation for magnetic fields. Study of the pattern formed by the iron filings shows continuous lines of force exiting the bar at one end and entering at the other. The two ends of the bar magnet have been arbitrarily named as north and south poles, with the lines of force exiting from the north pole and entering again at the south pole. Another experiment often conducted places two bar magnets in different configurations to prove the well-known expression that like poles repel each other and unlike poles are attracted to each other.